Tier 1 carriers operate the circulatory system of the global economy, investing billions into 5G standalone networks and optical backbones. Yet, despite this massive physical capacity, they struggle to guarantee a specific packet will arrive exactly when it needs to. These latency limitations stem from legacy TCP/IP and BGP routing protocols, which impose software bottlenecks regardless of the physical hardware's capacity. TCP/IP is the foundational suite of communication protocols that dictates how data is packetized and routed across the Internet. BGP, or Border Gateway Protocol, is the system responsible for directing those packets between independent carrier networks. This schematic of the standard 5G standalone downlink path shows the SMF directing routing rules. The SMF, or Session Management Function, is the core control node that manages user data sessions. It pushes these instructions via the N4 interface down to the UPF. The UPF, or User Plane Function, is the node that handles the physical packet forwarding toward the cell tower. As data passes through, it is encapsulated as GTPU traffic. GTPU, or GPRS Tunneling Protocol, is the standard method for wrapping and transporting user data across mobile networks. The failure begins when a burst of eMBB traffic hits the UPF. eMBB, or Enhanced Mobile Broadband, is the standard high-bandwidth consumer 5G traffic, such as video streaming. When this traffic, destined for the G-Node B, hits the UPF, the hardware blindly blasts these encapsulated packets toward the radio edge at line rate. A G-Node B is the physical 5G base station, or cell tower. The radio frequency environment cannot always absorb that sudden unbroken burst. The hardware at the cell tower, the BBU, has finite memory. The BBU, or baseband unit, is the hardware component at the cell tower that processes the baseband radio signals. Its buffers instantly fill to maximum, and excess packets drop off the edge of the queue. TCP detects network congestion through these dropped packets. When the drop registers, TCP halves its transmission rate, creating a sharp sawtooth pattern of collapsing throughput and massive, unpredictable jitter. That jitter violates the strict service level agreements required for URLLC. URLLC stands for Ultra Reliable Low Latency Communication, which is a high-priority network slice designed to support critical applications like remote robotic surgery and autonomous vehicles. To compensate for this localized buffer bloat, carriers currently spend billions in capital expenditure to over-provision localized midband and millimeter wave spectrum, deploying extra radio hardware to absorb the excess traffic. Attempting to resolve a reactive transport layer software flaw by over-provision extensive physical radio frequencies is mathematically futile and economically unsustainable. Solving this bottleneck requires a complete decoupling of the predictive intelligence of the network from the physical forwarding hardware. This architecture introduces the PTCP Global Orchestrator. It runs as a cloud-native Kubernetes cluster alongside the 5G core. Kubernetes is an open-source system for automating the deployment, scaling, and management of containerized applications. The orchestrator continuously pulls in live telemetry from the UPF, mapping current routing states against the real-time buffer limits at the local cell towers. It processes this data using PaulTT algorithms. PaulTT, or Pattern of Life Tensor Train, is a mathematical modeling technique designed to predict high-dimensional traffic behaviors over time. These algorithms calculate the exact impending traffic load for every distinct network slice. They independently map the expected surges of consumer video against the sparse, hypercritical telemetry of URLLC traffic. The output of this calculation is a bounding policy envelope. It generates a strict pacing schedule for the network before any physical congestion ever takes place. Instead of waiting for a cell tower to signal a buffer overflow, this envelope identifies microscopic gaps in the radio frequency spectrum milliseconds before the data physically transmits. By predicting traffic horizons instead of waiting for dropped packets, the carrier control plane operates as a proactive, predictive actuator. That predicted schedule must be executed directly on the physical UPF node, whether that node is a COTS server or a hardware DPU. COTS refers to commercial off-the-shelf hardware, while a DPU is a dedicated data processing unit designed to offload networking tasks from the main processor. A lightweight memory-safe daemon deployed on the UPF host ingests the quantized pacing schedule sent down from the global orchestrator. This diagram shows the daemon loading that pacing logic directly into shared memory maps using eBPF. eBPF, or Extended Berkeley Packet Filter, is a technology that allows custom programs to run safely and natively within the deepest layer of the Linux operating system kernel. As new GTPU encapsulated packets hit the physical UPF network interface card, the eBPF agent intercepts them immediately at the XDP layer. XDP, or Express Data Path, allows the kernel to process incoming packets instantly upon arrival, before the operating system allocates memory. This bypasses the standard TCP IP stack, eliminating complex routing lookups and heavy CPU processing overhead. The eBPF agent holds and releases the outgoing packets to match the orchestrator's schedule, executing this pacing in O1 time. O1, or Big O of 1, is a computer science term meaning the execution time remains constant, regardless of how much total traffic is hitting the server. Every packet's downlink egress is precisely paced in single-digit nanoseconds. This mathematical pacing at the XDP layer establishes the UPF as a deterministic traffic regulator. Let's observe the execution of this architecture when a high-margin URLLC network slice shares hardware with a commodity eMBB slice. This timeline charts a sudden microburst of consumer video streaming slamming into the UPF, represented by dense blue packets crowding out a red packet. Below, because the orchestrator forecasted this surge, eBPF agents mechanically spread out the blue video packets, carving precise microgaps. A critical red URLLC packet carrying sensitive robotic surgery telemetry arrives at the UPF during the peak of this burst. Instead of waiting in a congested buffer, the red packet encounters zero queuing delay. It drops perfectly into one of the pre-calculated open slots. The interleaved traffic stream arrives at the G node B perfectly synchronized. Because the volume never exceeds the radio's capacity, the cell tower buffer never overflows. This mechanical interleaving mathematically guarantees the isolation of the URLLC slice, achieving absolute determinism over the air interface without dropping a single packet. Because this relies on standard Linux eBPF, the execution is hardware agnostic and scales from the localized 5G edge to the broader global routing backbone. This provides the same pacing architecture for massive IXPs and transoceanic submarine fiber cables. IXPs, or Internet Exchange Points, are physical networking hubs where different telecommunication carriers connect their backbones to exchange traffic. Regional orchestrators compress their local network state data using SVD. SVD, or singular value decomposition, is a mathematical technique used to distill massive data matrices into their core predictive components. In this federation process, an orchestrator in Tokyo calculates the exact incoming traffic horizon for a peering link in Los Angeles, transmitting that intelligence milliseconds before the physical packets cross the Pacific Ocean. Armed with that global horizon, carriers can continuously interleave international traffic flows, driving their existing undersea fiber cables up to 90. At the peering edge, eBPF agents detect and drop anomalous DDoS traffic natively at the XDP layer. Malicious volume is neutralized in O1 time, shielding the core routing fabric. Federating this intelligence shifts the global network away from blindly absorbing intercontinental data surges, structurally interleaving global data flows before they converge. System-wide integration of this pacing architecture alters the capital and operational expenditure trajectory for a Tier 1 carrier. This chart details the economic yield. By doubling the usable capacity of existing physical networks, a global carrier can defer an estimated $3 to $5 billion in optical and undersea networking capital expenditure over a 5-year horizon. At the 5G edge, eliminating radio frequency buffer bloat increases effective cell site throughput by up to 20%. Squeezing more bandwidth out of existing spectrum delays the need for localized tower densification. Operating expenses drop as carriers phase out legacy DTI appliances. DPI, or Deep Packet Inspection, involves expensive security hardware that opens and analyzes data packets to filter out malicious traffic, a process that becomes redundant as threat mitigation moves into the kernel layer. Carriers leverage legally binding zero-jitter SLAs to monetize network determinism, moving past the low margins of commoditized bandwidth. This unlocks high-margin revenue from HFT firms, autonomous logistics operators, and hyperscalers requiring lossless, all-reduced transit. HFT, or high-frequency trading, is a financial strategy that relies on executing millions of orders in fractions of a second. Hyperscalers are massive cloud service providers, like Google or Microsoft, that operate networks of data centers globally. All reduce is a synchronization step in distributed artificial intelligence training, where data must be aggregated across remote data centers without a single dropped packet. Combined, this creates an estimated 3-year system-wide return on investment between $5.4 and $9.1 billion in capital deferral, operational reduction, and new enterprise revenue. By embedding predictive mathematics directly into the operating system kernel, telecommunication providers escape the limits of reactive physics and establish themselves as the deterministic foundation for the modern digital economy.